Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. This video is about V-belt. V-belt is one of the machine element in machine component design. Beside gears, V-belt is also a power transmitter or torque transmitter. The power that is transmitted from one pulley to the other pulley by means of the friction between the belt and the pulley. The advantage of V-belt over gears is that it can transmit power to a longer center distance. It is also far more economical compared with gears. But the advantage of gears is that gears have better efficiency because gears can transmit power, almost all the power from driver to driven in very high speed. The reason to choose V-belt because of low cost compared with gears. As you can see, for gears, if we want to go for longer center distance in a power transmission, we need a lot of stages of gears. But for V-belts, we only require 2 pulleys and a belt. The advantages of V-belt over flat belt are V-belts can transmit more power because we can use multiple V-belts on the pulley compared with flat belt. The drive of the V-belt is positive because the slip between the belt and the pulley groove is negligible. The V-belts are also made endless. There is no joint because we use standard length provided by the V-belt manufacturer. Therefore, the drive of the V-belt is smooth and the life is longer compared with flat belts. Since the V-belt drive is smoother than flat belt drive, so the operation of the V-belt is quiet. The name is V-belt because of the cross-section shape. It's kind of V shape, and they have a base rubber compound and also the reinforced steel wire. The reinforced steel wire is to strengthening the V-belt during power transmission. They also have the protective cover. Normally protective cover is a kind of layer made by plastic. This protective cover is in terms of endurance against high temperature during the power transmission. Basically, there are 5 types of section in V-belts, which are A, B, C, D, and E. And the dimension of this various section of V-belt can be seen in this image. So this categorization is normally based on the cross-sectional size that we need and also the amount of power to be transmitted by the belt. Actually, in industries, there are many V-belts manufacturers. One of the V-belts manufacturer in industry nowadays is Mitsuboshi. So in this lesson, we will use Mitsuboshi as our reference for our V-belt selection. Okay, the procedure for selecting V-belt is firstly we need to know set the input speed, the drive, and also the driven output speed, and we need to set the input power, transmitted power HT, and we need to set the initial center distance of between the 2 pulleys. Also, we need to what type of machine gonna use for this power transmission, and also how many hours per day we're gonna use for this pulley and belts. Another thing to mention in V-belts is about the speed ratio. Since we have 2 pulleys, the smaller pulley and bigger pulley, and 1 is input speed and 2 is output speed. Diameter 1 is for smaller pulley and diameter 2 is for bigger pulley. And the input is a driver and the output is a driven. Since the tangential velocity along the belts remain constant, so basically N1 times D1 equal to N2 times D2. So speed ratio is N1 over N2, which also equal to D2 over D1. Also we can call it bigger diameter over smaller diameter of the pulley. So let's say input is 400 RPM, so we want the output to be 200 RPM. So our speed ratio is 400 over 200 or 2, or equal to D2 over D1. let's say we want the smaller pulley to be 3 inch, so the bigger pulley, the diameter is 6 inch. Okay, this is a typical V-belt problems. As you can see in this image, so we have a system here of two pulleys. One is small diameter, one is bigger diameter. So the small pulley is a driving pulley connected to a motor of 5 horsepower of 750 RPM. So our input speed N1 here is 175 RPM. So this machine drive an aggregate mixer machine at 875 RPM. So the bigger pulley is connected to a aggregate mixer machine, and the output speed N2 is 875 RPM. So it means that our speed ratio here is 2. And also this machine operates for 16 hours per day. The diameter of both pulley is not given, so it means that we have to design. What is given here is the initial center distance is given here of 12 inch. So if you look, the first step that we have to do to select the V-belt is we have to compute the design power, HD. The HD design power is not the power shown here. The 5 horsepower is not the design power. The 5 horsepower is transmitted power, HT. So the HT transmitted horsepower have to multiply by certain factors to get our design power HD. The reason of not choosing the transmitted power, which is 5 horsepower in this case, is because the transmitted power is direct from the motor. Since in this system the pulley is connected to V-belt, and the V-belt is a standard V-belt supply from the manufacturer, so they have set certain factors which we got to consider for us to calculate the true power carried by the pulley. So this is why we call the design power. If you look from the Mitsuboshi guide for selecting V-belt on page 1, there is a formula where you can calculate design power HD, where HD is equal to HT times KS, where HT is the transmitted power and the KS is the service factor. Okay, to get the service factor of KS, we need to know the other 3 factors, where KS equal to KO plus KI plus KE. KO is the service correction factor. We can get it from table 1.1. And KI is the idler correction factor. We can get it from table 1.2. And the KE is the environment correction factor. We can get it from table 1.3. To get the service correction factor KO, we need to refer table 1.1 on page 2. If you look in this table 1.1, so we have 2 conditions here, driven machinery and also the driving unit motor. So if you look in the area of driven machine, we have 4 categories here, 4 rows. The first row for light duty machineries, as we go down until the 4th row, there's more on the 4th row is more on the heavy duty machineries with heavy impact and so on. So since in our case our machine is pulley is to drive aggregate mixer, so it will be fall into the second row, because second row, if you look on we have door mixer, like it's kind of not like duty machinery, it's more on between medium duty and light duty, so it should fall in the second row. And if you look at the driving unit motor area here, we have 2 columns. One is for type of motor we use. The left column is for the maximum power is less than 300% rated power, and the right column is for maximum power is more than 300% of rated power. In our case, we are not given what type of motor we use, just stated that the power from the motor is 5 horsepower. So normally in general case we will use the left column here. Okay, if you look in the left column of driving unit motor here, we have a sub column of running times, which is the left is 3 to 5 hours per day, the middle column is 8 to 12, and the third column is 16 to 24 hours per day. So in our case, our running time of our machine will be 16 hours per day. So we will select the third column. So by knowing our driven machine, which is aggregate mixer machine, and also the running time of the machine is 16 hours per day, so the service correction factor KO is 1.3. The next thing is to find the idler correction factor KI. KI we can refer to table 1.2. To explain about this idler correction factor KI, as you can see, when the two pulleys is running in counterclockwise, in this case, we have the top side of the belt is in tight condition while the bottom side is in loose or slack condition. So through times, the belts will elongate. When the belt elongates, it begins to slip. So this will accelerate the belt and pulley wear and reduce its efficiency. In order to solve this, instead of increase the center distance of the two pulleys, the engineer will put an idler as shown here as a tensioner to tighten the belt. An idler is a kind of small pulley which is fitted to this pulley and belts. Okay, if you look back at this table 1.2, we have 4 cases of idler to get our idler correction factor KI. So the first case is belt slack side inside of belt. So what does it mean? It means that the location of the idler is on the slack side of the pulley and belt, as shown here. So in our case here, it is at the bottom. It also means that the location of the idler is inside of the belt, as shown in this image. In our second case here, the belt slack side outside of belt, which means that the idler is still at the bottom, but the location of the idler is outside the belt, as shown in this image. In the third case, belt tight side inside of belt. This means that the location of the idler is at the tight side, which is at the top, and the idler is inside of the belt. And lastly, the fourth case means that the location of the idler is outside of the belt. Okay, since this problem, there is no idler added to the system, so the idler correction factor KO could be neglected, so the value of KO is 0. Okay, for the environment factor KE, we have to refer table 1.3. If we look at this table 1.3, all the environment conditions like frequent start and stop of machine, hard to conduct maintenance checkup, dusty environment, high temperature, and oil or water splashing, we must use the value of KE 0.2. As in our case, it is not stated the kind of environment of the machine, so our value of KE is 0. Okay, since the value of the service factor KS is equal to KO service correction factor plus KI idler factor plus KE environment correction factor, so our value of KS service factor is 1.3. Okay, since our design power HD is equal to HT, the transmitted power, which is 5 horsepower, times the service factor KS. So our design power HD is equal to 6.5 horsepower. Okay, after we have calculated our design power HD, our second step is to select the belt type. Remember earlier that I've mentioned V-belt have 5 types of section, which are A, B, C, D, and E. By knowing our calculated design power HD, which is 6.5 horsepower, and the input RPM of the small pulley, in our case is 1750 RPM, we can select the belt type from figure 1.1 on page 3 of your Mitsuboshi guide for V-belt selection. If we look in this figure 1.1, we have 5 zones of belt types for us to select, which are A, B, C, D, and E. The x-axis is the design power HD, the unit in horsepower, and the y-axis is the small pulley speed in RPM. If we study the distribution of the zones, it looks like type A zone kind of occupying major area in this zone distribution. It is kind of like if we move toward the bottom right corner, we are focusing to zone type E. So it means that if our pulley and belt system is high RPM and low horsepower, we will fall into category type A. And if our system is very high horsepower but low RPM, we will fall into category type E. Since our design power HD is 6.5 horsepower and our small pulley speed is 1750 rpm, we are in the zone A, so we will select type A. Also to mention here is that type A is the smallest cross section and type E have the biggest cross section. Since type A has the smallest cross section, the power capacity that it could carry for one belt for this type A is quite low compared with other types because of its small size. By the way, type A is much cheaper and we can overcome this by adding more number of belts to carry the load required. So it will be explained later in this V-belts design problem. Okay, the third step is to select the pulley size. Since both pulley diameter are not given in this V-belt problem, this means that we have to begin by selecting the diameter of the small pulley. The diameter of the bigger pulley will be known because the speed ratio is 2. So how do we select the diameter of this small pulley? Since we have already selected type A for our belt, so we will refer to table 1.4 on page 3, as shown here. If we look at this table, in this area we have minimum pulley diameter for each section type A, B, C, D and E. Logically, since type A has the smallest cross section, the minimum pulley datum diameter is the smallest compared with the other types. Since we have selected type A, we will use the diameter of 3 inch. Okay, since the small pulley diameter is set to 3 inch and the speed ratio is 2, our bigger pulley diameter is 6 inch. Okay, the fourth step is to determine the belt length. Since we have set the diameter of both pulleys of 3 inch and 6 inch, we can determine the length of the belt by using this formula on page 3. Okay, this formula shows you how to calculate the interim belt data length or our initial length. C prime is our initial center distance, where in our case is 12 inch, where the capital DD is our bigger pulley diameter 6 inch and the small DD is our small pulley diameter 3 inch. By substituting all these values into this formula, we will get our LD prime, our initial length, 38.13. Our next move is to refer table 19 for selecting type A standard belt length. This table is on page 6. This table have all the standard length provided by Mitsuboshi for type A belt. In this table, we have 3 columns, the belt code, the outer length and the datum length. The length that we select in this table is the datum length, not the outer length. Since the thickness of type A section is 0.31 inch, the datum length is slightly less than the outer length because we are measuring the inner perimeter of the belt length. Okay, since our value of the initial belt length LD prime is 38.13, we will refer to the nearest standard length provided here, which is 38.3. As our standard length of the belt LD is 38.3, our center distance will be adjusted and it's not 12 inch. So the formula to calculate this new adjusted center distance C can be shown on page 3 in your Mitsuboshi guide. The formula to calculate the new center distance C is shown here. If you look at the equation, we have variable B, where B is stated in the second equation. As our standard belt length LD is 38.3 and our bigger diameter pulley diameter is 6 inch and our small pulley diameter is 3 inch, we could calculate our new center distance C. After we have put all the values into the equation and compute for C, the new center distance C is 11.988 inch. This means that when we design our power transmission system, the 2 shafts where we mount our small and big pulley, the distance between the shaft is 11.988 inch. Okay, lastly is to determine the required number of belts. We have already calculated our design power HD with the value of 6.5 horsepower. And the belt that we chose is type A, based on the 6.5 horsepower and the speed of the small pulley 1750 rpm. If we refer to the table 115 on page 11, they have all this basic power rating for one belt. If we look in this table, we have three columns here, which are small pulley speed in RPM, the basic power rating per belt, HS, which is based on small pulley diameter in inch, and additional power rating HA, which based on the system speed ratio. Okay, the equation to get the number of belt required is HD over HC, where HD is our design power 6.5 horsepower and HC is corrected power rating per belt. To get HC is equal HS plus HA times KC. HS is the basic power rating per belt and HA is additional power rating per belt, where we can get it from table 115 as shown previously. KC is a power rating correction factor, which will be explained later. If we look at this table 115, to get HS, our basic power rating per belt, we go for minimum pulley diameter 3 inch. Since our minimum pulley diameter is 3 inch and the speed of the small pulley is 1750 RPM, so for the speed of 1750 RPM, we need to do an interpolation so that our value of HS is 1.68. For HA, additional power rating per belt, since our system speed ratio is 2, we refer to the last sub-column here, where for the speed ratio greater than 1.57. For the speed of 1750 RPM, we need to do an interpolation as well to get the value of our HA 0.5. Okay, if you look into this equation, HC is equal HS plus HA times KC. We already got the value of our HS and HA. The next move is to find the KC. KC is the power rating correction factor. KC is equal K theta times KL, where K theta is arc of contact correction factor and KL is belt length correction factor. We can get K theta value from table 16 on page 4. In this table, we have three columns. The first column is the ratio of DD minus DD over C, bigger pulley diameter minus small pulley diameter over C. The second column is the contact angle on small pulley. The third column is the value of K theta. We have two ways to get this K theta value, either by taking the ratio of DD minus DD over C, or we can calculate the contact angle. By the way, to calculate the contact angle of small pulley, we can use this formula as shown here. As you can see in this image, contact angle means how much the angle the belt will wrap or contact with the pulley. As you can see, the first formula is for contact angle of small pulley. The second equation is contact angle for big pulley. To get the K theta value, we only need to calculate the contact angle of small pulley, so we only use the first equation. By the way, the easiest way to get the K theta value is to use the first column, because we only need to get the ratio of DD minus DD over C. So the value that we got from this ratio is 0.25. Since the K theta value in this table is a factor, we don't have to use interpolation. So for ratio of 0.25, the nearest K theta value that we got is 0.96. Next is to get the belt length correction factor KL. We can get KL from table 17 on page 4. In this table, the first column is length designation or our belt length, and all the other columns are each section type A, B, C, D, and E. Since our belt length LD is 38.3, we are in this category. And we use type A for our belt, so our KL value is 0.89. As our KC, power correction factor, is K theta times KL, our power correction factor KC is 0.854. Therefore, we can get our corrected power rating per belt HC with the value of 1.862. Finally, the number of belt is equal to HD over HC, where HD is our design power that we got is 6.5 horsepower, and HC is the corrected power rating per belt that we got is 1.862 horsepower. So the number of belt required is 3.49. So if we round out the figures, the number of belt is 4 pieces. So we need 4 pieces for our Type A section of V-belts. Alhamdulillah, we have done our V-belts problem. I hope you guys understand this video explanation about V-belt selection using Mitsuboshi V-belts. Inshallah, there will be more video coming soon. Please stay home and stay safe, and Ramadan Al-Mubarak. Dan juga kalau makan masa buka puasa tu baca bismillah dulu.